and gents. We're just about ready for the final team presentation. Who's hiding in the side room? Who do I need to come and get?
Full house.
Can we start? Thank you. Okay, so welcome everyone. We are Team CranSEDS, students from Cranfield University, Skolkovo, Moscow, and Sabatier, France. So we're 3 school and 1 team, and we're here to present Project Dragonfly.
Thank you, Manish. Sorry for the lack of creativity. I guess you've seen this picture for like a couple of times today. But just to summarize the top-level requirements that I'm pretty sure you know well. Basically, Alpha Centauri is 4.3 light years from here. We have to reach that solar system, star system, within 100 years using laser sail. Has a propulsion system and using laser subsystem power not higher than 100 gigawatts. Starting from this point, we analyzed basically, of course these are the main requirements of the mission, but that path is actually a gold mine. And we can provide a lot of scientific information, very, very valuable for the research. So we analyze which kind of physical quantities we can get along our path. And we recognize, for example, the density of the interstellar medium, the composition, the magnetic field, and once arrived in Alpha Centauri, of course also the gravitational field is there. This could be very useful to identify actually the presence of planetary system orbiting around that binary system, a star system. And in case of presence of these planets orbiting around that, it could be also very interesting get information about the morphology, the composition of these planets. Once identified this physical quantity, of course we recognize which are the scientific payload that we have to carry with us, and identify the design that for best can provide this kind of information. We identified 4 different designs that after that we analyze in order to understand which is the most reliable and feasible among them. The first one, 6 probes, basically is based on a mothership deploying 6 different probes along the path at different places in order to get information measurement all along the journey. The second one, called relay station, basically is based on a relay station orbiting around Pluto that, carrying scientific payload, can study the border of the solar system and in some condition can help us to communicate with the Earth. The third one is called 3 generation, basically is made by 3 main spacecraft launched every 30 years, one from the other. It could be very useful because it increases a lot the communication and the reliability of the overall mission design. The fourth one, multiple lens. Of course, the size of the lenses for this laser subsystem is one of the most tricky part of this mission. Using more than 1 lens, we can reduce the actual size of these lenses. In order to have like objective analysis of this kind of these 4 design, and in order to identify which is the best and the most feasible, we produce a trade-off analysis considering 4 different like area of interest, so mission, spacecraft, laser subsystem, and communication subsystem, and we analyzed many parameters for this field. I would like to point out the value under each parameter because they represent the risk related to a failure in that specific area of the mission and the importance of the overall mission, the second number. Just want to point out the value, so the importance of the scientific value of the mission, that of course is one of the most important information we can get, and the reliability and the risk related to the communication link. Why I'm pointing out this 2 factor? Because basically these 2 factors make us to decide for the 3 generation design. With this kind of design, we can improve dramatically the scientific return. Launching 3 main spacecraft, 30 here, one after the other, we can update after getting heritage actually from the previous mission. We can update the scientific payload, the mass of the spacecraft, and so have higher reliability. Moreover, we have also higher redundancy, of course, because we have 3 spacecraft and not only 1. And last but not least, of course, we have easier communication because we can use the farther main spacecraft has a relay station to send the communication link back. So basically, the 3-generation design was the design that we choose, considering also a little bit of the relay station because of this capability of relay the communication. I'd like to introduce Honor, is going to present a little bit more in depth the
Yes, thank you, Andrea. And the 3 generations, as you can understand the name, it consists of 3 spacecraft which will be launched with 30 years of frequency. 3 spacecraft is going to focus on different aspects of the star system. Our main aim is to understand the star system in general. Then they focus on the double star system of the Centaur A and B. And another important issue and another advantage of this architecture is that we will take an evolutionary approach for the next mission, and we will use the technological improvements within that 30 years, new scientific findings with the ground-based and from the previous spacecraft, and also maybe secure a budget for the next one. And the 1st generation mission is going to focus on the understanding the star system in general, and it's going to target the Alpha Centauri A and B L1 point. It is a stationary point, as some of you may heard of it. So it's a Lagrange point, and it is basically an interaction point of 2 star winds, and we might be able to see how these star winds are interacting with each other and how their interaction affects the star system in general. And this mission can be seen as a precursor for next mission, as we will target the individual star systems for the individual stars for the next missions. And the duration for this mission is determined as 11 years or more, depends on the propellant we have or the spacecraft availability, basically. This is because of it's a half a solar cycle. These are stars, and we may expect a similar behavior in these stars, and we believe that 11 years will be enough to observe that. So the 2nd generation is going to target the Alpha Centauri B from the literature, which is about the size of the Sun, and there is a speculation that there might be a planet orbiting around it, which is not expected to have a life on it, but still it's checking how it is interacting with these 2 stars and within this star system. Again, the duration is determined as 11 years, which might be changed with this new scientific findings, but it is a base value we would like to determine in the first place. And the 3rd generation is going to target the Alpha Centauri A, which is bigger than our Sun. And we will use the data from the previous 2 spacecraft in order to, before get close to this star, in order not to melt the spacecraft or find a suitable operational orbit before that. And the duration is again determined as 11 years, but it is subject to change based on the scientific findings. And the laser structure is going to be explained by each one.
As we know, every cell needs its wind. Our wind is made of light. And to produce it, we need to create a laser. And as we can see, we have a lot of possibilities. We have to choose between a lot of types, the most suitable. Some of them are quite unfeasible. For example, gas laser needs a large volume that we have to carry to produce the laser, or the chemical one requires a particular condition of pressures and temperature that are quite challenging to create in space. So we had to do a trade-off to decide which type of laser is more suitable for our mission. The 4 parameters that we have decided are the cost, obviously, that has quite a low weight because all the mission will be very expensive. but we have more important parameters that will influence the final project. The TRL is another big issue, but since the date of the mission is quite far, there is the possibility to improve our technology, considering also that right now the technology about laser is increasing and being very fast. Maintenance and the possibility of repairs. This parameter will also influence in which orbit we will place our laser. The weight is quite high because the laser will have to work for a lot of time. So it is mandatory to have. It's mandatory that it is reliable, but also be able to be repaired. Last is the efficiency. Since we are producing 100 gigawatt laser, we have to find the most efficient one, unless we will basically have kilometers and kilometers of solar arrays. The winner is a fiber laser, and then we have to decide where to put it. These different possibilities have been chosen thanks to a trade-off. As we can see, the winner is the Lagrange point 1 between Sun and Earth, because putting it in L4 or L5 could be difficult for repairing and maintenance. And Geo and Leo, maybe public opinion will have problem to put a laser that could just obliterate out of Parliament from the orbit. That is quite good. We don't want to be the new guy, folks. Last decision. Now we have to explain how this laser will work. We will use different laser pumps, and we will collimate the beams thanks to collimators to produce a beam that will pass through the lens and arrive to our probe. We had to decide for the lowest possible wavelength, because related to the wavelength there is the problems related to interference and diffraction. Smaller the wavelength, less will spread our beam, basically. And for the one of you that are quite concerned about the Earth, if we point our laser to the Earth, the power is quite low, the power delivered is quite low, less than our Sun basic radiation. So it will be quite reliable, and we will not annihilate anyone.
So after having seen that how the laser system would work and where it will be placed, we look into the sail parameters, how we define our sail. So basically we need high acceleration, we need to accelerate to a fraction of speed of light. And to do so we need to look into material which will allow us to do that. So we looked into material which have low density, high reflectivity and high operating temperature. Well, these are some of the materials that were mentioned by Geoffrey and Matloff, and we chose finding 5. Among these, well, you can see that silicon has really high reflectivity. Well, we cannot use that because it works only above wavelength of 1100 nanometers. So next best is silicon carbide, which is 56% reflectivity. So we went along with this one for our sail. Again, the acceleration doesn't just depend upon the material property of the sail, but also on the output laser power. So these are the parameter of the silicon carbide. It has low absorptivity and high emissivity. Next, we need to see how big our sail would be and how big the laser aperture would be. So we came across this, we did some mathematical calculations and we saw an interesting graph. And this graph, as you can see, if we have a sail of 1 kilometer, it gives us a laser aperture diameter of more than 400 kilometers, which is not really desirable. So we looked into an optimum of 183 kilometer laser aperture diameter, giving us a sail diameter of 4.6 kilometers. But how fast are we going to accelerate with this diameter of sail? So here you can see a graph which shows the diameter of this sail and the acceleration relation between the two. And turns out we can accelerate with 0.13 meter per second square. And if we have this acceleration, how long will it take to complete the mission? Well, so we saw that 0.13 meter per second square acceleration. It takes about 3.6 years to accelerate to 5% of speed of light. And considering the deceleration time, we plotted a graph to see how the timeline would change. And this is a relation between the acceleration and time required. And you can see that with 0.13 meter per second square of acceleration, we can accomplish our mission within 98.17 years. And so what do we do there once we have accelerated and at Alpha Centauri?
So, yes, once we reach Alpha Centauri, we want to slow down our probe. As we are cruising with 5% of speed of light, if we would not slow down, we would pass through the entire Alpha Centauri system within a few days. After 100 years of travel, that's not such a favorable option, so we'd like to slow down, enter an orbit, and have basically unlimited observation time from this point of view. So how do we do that? We basically have the same delta V as for acceleration. So there are also like the same possibilities on a first glance view. You have, for example, chemical and electrical propulsion drops out for the same reason as it dropped out for acceleration. It's simply much too heavy. These would be smileys crying. Then next option we looked at was using the light sail and the laser system again, which is kind of could be a good idea as it's already everything there. But when looking further into it, we've seen that due to the huge distance we have when decelerating, it doesn't seem to be very feasible anymore. There are ideas in papers to like separate a piece of the light sail and use it as a reflector, so that the laser comes from the correct direction to decelerate it. But the whole system seems to be extremely fragile, controlled over a distance of 4 light years. Well, not so good. So finally we went for the magnetic sail, as other groups as well, which actually acts as a brake, so we don't need any additional energy for it, but we just take energy out of our system, kinetic energy. So how does a magnetic sail work? We've seen it already as well. We produce basically a magnetosphere around our spacecraft, which will then interact with the environment and braking against the environment. Also, by changing the attitude of the whole spacecraft, we can basically give a lift and steer it left, right, up, down. So now, how does it perform? We made some assumptions. You can find them in our report in detail. And what turned out was this graph here. So we would be able to decelerate from 5% of speed of light here in year 0 within 20 years towards orbital speeds, which are in the order of some tens of kilometers per second. So how do we do it? As other groups have seen it already as well, a magnetic sail basically works well as long as we are fast. Once we become slow, the deceleration is not so massive anymore. But what finally saves us is as soon as we enter the local heliosphere of Alpha Centauri, the magnetic sail will work against the solar wind of the suns there. So what happens in the last moments is, in this graph, at 20 years, we basically enter the heliosphere, which means that from then on we have the solar wind streaming towards the spacecraft, so we have an additional delta V between surrounding and spacecraft. In outer solar system, the density is lower than interstellar medium, so we have basically a period of nearly no deceleration. Whilst once we get closer to the suns, the density increases massively, and it decelerates nicely down. We would even, depending on how we set the parameters, it would even be possible to like leave the system again. So that also means that once we are close to the sun in a close orbit, we can use this mag sail by changing the attitude or the strength of the magnetic field to navigate within the system to change orbits and observe different spots. So, next topic to be considered is the communication. We've already seen it shortly when looking at the different mission architectures, that we will have 3 spacecraft following up each other. The following spacecrafts can act as a relay station for our communication link. That finally gives us just several backup modes for communication. So, of course, there is the possibility to have a direct link. If the direct link fails for any reason due to bad attitude control or whatever, or decreased power, we do have backup possibilities by using the other spacecraft as relays. As well, we would go for optical communication systems, as other groups as well, just as it has certain advantages in power consumption, in size of the components. As a wavelength, we went for 850 nanometers, which is basically a wavelength that is available now in off-the-shelf products. We've seen that for uplink, we don't really need a lot of data rate, probably. It would more be for attitude control, for navigation and orbit control, whilst we need the high data rates for downlink then. So what does it consist of, the communication system? Of course, we'll have a source. We finally also ended up at phased array laser diodes to power our communication. Then we'll have the antennas to receive it, which are basically telescopes, optical systems, looking at the signal coming down. And of course, what is a big topic here is the attitude control, or the beam steering, as the beam should be as narrow as possible to not lose too much energy to have a high SNR. Yeah. So the mission timeline is, in case if our first visit starts from 2050, our mission is going to end by 2226, in 100 years. Individual spacecraft will reach the other star system in 98 years, and overall, all 3 visits is going to end in 160 years in total. And all missions are based on the idea of the same as designed the first one. 2.6 years of acceleration, about 75 years of cruise, and about 20 years of deceleration, and about 11 years of operational time. And with this, we can come to the conclusion that our design, we offer a 3 spacecraft system, then we will have multiple tries if you secure a budget for that, for all 3 of them. And we might have a better communication, as we have 2 options, inter-satellite link or a direct link. We allow our spacecraft to be upgraded for the next generations. And we offer 3 tons of spacecraft with a magnetic sail and light sail. And mission is about less than 100 years for individuals, and our whole mission in 160 years. And with this, I'd like to thank you for your attention, and on behalf of my team.
Okay, so I've got some questions. Very good presentation, thank you. So let's deal with your 3 generations.
Yeah.
So every 30 years you're launching a new vessel. So you launch one at 2050, you launch one 30 years later, and another one 30 years later.
Yeah.
And by the time the final ones reach the destination, 160 years passed.
Yeah.
So first of all, explain that to me, because are they all traveling at different speeds?
No. Well, the base is determined. Actually, a second and third generation in this case is there is a baseline is determined for that,
right,
which is the first one. Actually, we assume that 2.6 years would be the base or nominal. Might be increase. We don't consider increase, but we mostly consider decrease in that acceleration and cruise period and reaching period, basically, with the technological improvements. Our spacecraft design mostly focused on the first one, and we determined the base values and nominal values for the second and the third one. And what we aim is to.
So what's your cruise speed? First one again.
5%. 5%. Yeah.
Right. So are you saying the others might go faster?
But yeah,
okay.
it's possible. Yeah.
So obviously every 30 years is a long time.
Yeah.
So everything's going to improve, as you've acknowledged, but also propulsion technology. So and this is the old obsolescence problem that you could launch later, you can go faster. Potentially, so your third one can end up taking over your first one.
Possibly, yeah.
So I mean that's not a reason not to go, because I think you should go anyway. But my point is, 30 years, the technology leaps in that time frame could be so large that it's quite a time frame to wait. Why did you choose 30 years and not say 10 years?
Actually, the reason is that the finding 100 years of plan and sending the spacecraft, all 3 spacecraft within 100 years, could be. Second and third could be sent by maybe 10 years of separation, but this is the base, and sending the spacecraft within 100 years. It's kind of a mission plan, like a 100-year plan for like a space agents or something.
Okay, so I mean, if for example the technology rapidly evolved, you think that you could change that? The later generation would say, actually, we weren't meant to launch until another 20 years, but we're going to try and launch it in 5 years instead because the technology has come on so far. Or do you think the future generations are going to stick to this roadmap?
So the thing with us is that we are in this case mission architecture is determined in a bit of conservative way. Basically, the way it is done today, a mission is proposed and it takes almost 25 years to realize. Sometimes, considering the Rosetta is proposed in like 90s and launched in 2004, and which takes some time. So that's one of the reasons we put 30 years, and the technological improvements is applied mostly within 10 years or sometimes 10 to 15 years. That was the reason we put 30 years actually.
Okay, my next question.
Can I just pursue that one? I take it you would have to leave at least 10 years between missions, because if you want to use the results of the first one to steer the second one, you're going to need 9 years just in communications links to get the information back to Earth to make the decision about how to steer the second one coming in. Would that be correct?
Yes, actually that's correct. But in this case, we considered certain autonomy in the software. Basically, not in a complete autonomous spacecraft, but in a certain autonomy in terms of attitude control and a bit of navigation, actually.
So there would at least need to be a communication link between the first and the second, so the first can tell the second the information it needs.
Yeah.
So there's a trade-off between launching too soon and waiting too long. So you want to, I would have said 30 years is quite long, but that's the decision you made. So, okay, so next question. The mag cells. So you had this chart showing your deceleration. And for a whole year, like 19.6, 20.6, it's basically just linearly dropping very, very slowly. This is the max cell exponent. And then you obviously get a massive increase in density, so the wind, and so it rapidly decelerates. Do you think that there's, you're not gaining much on that line, and yet you've got a whole year where you switch that mag cell on. What's the risk of failure in that period? Of the engineering system?
Well, I guess it's the same risk as before and afterwards during that time. The thing is, you cannot just switch on and off a mag cell with the switch, as it's a superconductor and the current is just looping. You do not actively power it up. You power it up once and then it's just running.
So do you see that as a risk itself?
I don't see this, well, it's actually not a year, it's like 0.2, half a year without anything. I don't see it as an additional risk, it's just a time where not much happens.
Okay. Next question, you had a graph. If you can go slides back, I forget which one it was. Keep going. I'll tell you what to stop. Keep going. Next one, I think. That one. Yeah. So you're calculating the diameter of the laser, which is that simple Valley formula. So Sean, why does it drop and then it climbs again? What's happening there?
Well, I think it's more because.
Well, the thing is, basically, we want to focus on our sail.
Mm-hmm.
So if you focus on a small spot, you need a bigger lens.
Mm-hmm.
So that means
But your wavelength is fixed for this.
Yeah, exactly. For this, our wavelength is fixed.
The cells are variable.
Yes, exactly. So, but
so why is it dropping?
So
it climbs.
So the thing is, if we have a really small sail, well, if you have a small sail, of course, we need a huge lens to really focus it in. Whilst if our sail is well, let's say if our diameter is too long, then finally we will accelerate for longer, and our focal point will be further away. So then our lens becomes bigger here.
Okay. That's me done. Thank you. James?
Yeah. How did you model the solar winds in the target star system that decelerates the max sail? Because the Centauri system is like a much.
Yeah, I took as a baseline our solar system information.
Okay, which is like correct because.
It was an assumption that it must be in this order of magnitude.
Mm-hmm.
Yeah, that's but that's a point for deceleration because you react with the local environment. Well, whether in interstellar space or in solar wind, you don't really know in advance what it exactly will be. So you would need a lot of surplus of power to have the flexibility there to react.
So what's the velocity after you use the max sail in interstellar space, and when you enter the Centauri system, what's the velocity? Roughly, it's like.
We would be here at around 10 to the power of 6 meters per second.
It's like 900 kilometers per second.
I guess, yeah.
So
it's still above orbital.
It sounds reasonable. I'm just thinking about the original report by Robert Zubrin, where he uses the max to get out of the solar system. So this is like the reverse process.
Basically, yeah.
So okay, it sounds reasonable. I'm just thinking about why I haven't considered this before because it's
well,
something
really wrong in that. But
well, when doing these calculations, I've seen that the whole thing is extremely fragile when decelerating in. So if you come a bit faster in, you basically pass by very quickly because the effective area is then really small.
Okay.
This area or this volume where the real braking occurs.
But you probably could still think about how you can tune the sail by injecting a higher current, for instance, in the system, etc., to give it a boost. So
I guess while still in interstellar medium, one would have really to control the power of the sail to go into the heliosphere with the perfect velocity.
And as you said, in terms of accuracy, if you come into the star system like a little bit with a kind of let me say.
Well, if you kind of miss it, then it's gone.
Yeah, but I mean, just if you miss it by, I don't know, 50 million kilometers or something like that, you probably have an area where this deceleration is feasible.
That's true, yeah. So this needs to be controlled, but at least from a spacecraft point of view, it can be controlled with attitude control.
Okay.
But it's a tricky part, deceleration.
I've got a more basic question about acceleration. So where's the point where your laser stops to accelerate the spacecraft? Is it like, I don't know, 100 astronomical units?
I think it's about 1,000 astronomical
units. It's about 2,000 something.
Okay.
I mean, that's for sure that we are outside of the solar system and a couple of orders of magnitude.
And your spacecraft mass?
It's about 3 tons.
3 tons.
So including the max cell and including the solar, including the laser cell, it's about 4,000, like 4 tons.
And your payload consists of
What?
The scientific payload.
Well, the payload, there are like some scientific. It's mentioned in the report, but we didn't really get it here.
It's not
in
the presentation.
We decided the payload basically considering the place where we are going to take to turn on the sensor.
Okay.
Sorry.
Sorry. Yeah. So these are the payloads that we would have on board the spacecraft.
Okay.
And related to this, I wanted to answer better to Mr. The payload is switched on, is completely automatic. We have a software that every time it reaches a place, a spot that is of our interest, switch on. Okay. Consider the cruise mode, switch to payload mode, and take datas. Then goes to the communication, and every time you enter a new box, you consider you check the system. If you have a problem, you go straight to emergency mode, and basically everything is automated. So you can read those. And that's it. So almost completely automated. So everything is done in the right spot. For example, if we have to turn on some payloads at the end of solar system or in the middle, and this will also help to not stress too much the components and the sensor, because you're using only some sensor each time, the most interesting ones, and sending the information when you are maybe at half the way, you will recover the data and maybe just start working for the next generation. Yes, basically it's that. Yeah.
Okay.
Yes.
Maybe there's somebody else who wants.
I had like a couple questions.
I also have
Real quick, I think you're on 47.
Yeah. So you want to go on
47?
Yeah.
Oh no, I wanted to look at the payload.
Yeah.
That one.
So does that include your? Okay, so when you have, there's a slide about the data data rates going back over your whole data system. If you could bring that. So you use all three of the spacecrafts to communicate back to Earth, or?
They can be used, yeah.
Yeah.
So does each one, so say you send out the first one, right? And you have 30 years to wait for the second one. That first 30 years, are you completely like...
No, it will have a direct link.
No, we have about the first one.
Yeah.
Okay, so is it in your payload mass, or is that in where? Where would that mass be?
Communication system.
Yeah.
There is a slides about
space
power.
I have, I think, mass and power.
Here, communication
Mass
mass.
budget? Yeah.
So you wouldn't have that 30 years like in a dark, you'd have to...
No, we still have data. For example, when it reaches the border of the solar system, we have data.
Okay.
a question about the laser system. You said you placed it at the L1 point?
Yep.
And
yes.
How do you counteract the 330 Newton power from just the photon impulse? Because the L1 system, there is no support there, and it's also unstable in one of the two directions.
Basically this is the main issue, putting something far away, and where if pushing the probe means also that you are pushing yourself toward the sun. But I think that having really big field of solar arrays in the middle of space could provide quite a good solar pressure on them. I'm not calculated, this part was not done by me, but...
Yeah, the person who did it, he's not here.
Yeah, so...
And you also want to bring this 180 kilometer lens to this L1 point.
Yes. Yes, it did. Yeah. No, it's not a good idea, but hey.
That kind of links into a question I've got, because you got this laser.
Don't break it because of bad luck for...
You've got a start laser 2050, so you've got to build 1,000 square kilometres of laser every year, now and then. That's roughly the area of London.
Lots of jobs.
I mean,
in space.
just shipping the water up there for the astronauts. Or you're going to use Technomagic's AI robots, which is but I mean, is it really practical to build a laser that big by 2050?
Well, actually, L1 point is not that far away, to be honest. It's 1 million kilometers. And I guess so on orbit, building capabilities would be improved by that. I mean, 2050 would be changed, actually, because laser system is still needs to be considered a bit. But well, on orbit manufacturing and building would be increased by that time, and we believe that we can do that.
What would you see as enabling technology to build that?
Sorry?
What would you see as enabling technology to build that?
Well, I mean, basically launches are increasing, commercial launches are increasing, and basically the cost is decreasing. I guess if laser system itself increases that TRL level to be built, then building it there would not be that problem, in my opinion.
So what about things like emerging asteroid mining, 3D printing, stuff like that? Do you see
well, the 3D printing is a big opportunity, of course. Asteroid mining, I'm not sure how we can benefit from it. But I mean, of course, these opportunities.
Laser test, for example.
Sorry, what?
Laser test. You can test.
You can play a game of asteroids.
So can I ask for clarification here? I understood that one of the starting assumptions of the study was that solar power satellites would be a starting scenario.
Well, not for us.
Am I right there, Kelvin?
Andreas, do you want to answer?
Yeah, it was one of the requirements. I mean, to base it on existing infrastructure. I mean, you could circumvent this requirement by saying, okay, there is some infrastructure in the solar system, and we just get it to
go with
the L1 point or something like that.
Yeah, I think fair enough. If you, Chris, if you're assuming you can make solar power satellites, this is of the same order of magnitude.
Oh yeah, right.
And the delta V difference between GO and L1 is not that great.
No, I speak as somebody who supervised a team of students who wanted to create a 1,500 kilometre shield between the Earth and the Sun to reduce global warming. I'm hardly one to really criticise it. It was just so big, you know, small space.
Then you use the energy for the laser.
Yeah, it depends on how you think technology is going to develop, really. I mean, and if you do have, artificially, intelligent, robots that are capable of constructing stuff, then you can just throw them into the solar system and have them go and build stuff. That's the techno-magic solution.
I forgot to ask, so the data rates compared for your 30 years, like your first 30 years, and compared to like your last 30 years, once you have all 3 spacecrafts in there. Did you have specific?
Well, we don't have the specific.
Well, yeah, I could not really answer straight away to that question.
Yeah, team member is not here who works
the communication system in the last slides of the communication. Maybe we have something on. Is there something? No. No. We had the communication system. No.
That's okay.
There was something.
Yeah, but the link from the spaceship direct to the Earth. So you will use optical communication. So what about the losses down the Earth's atmosphere? How could you control the signal back to the Earth?
Well, that's a topic, of course. I mean, the losses in general over these 4.3 light years. Finally, we haven't clearly defined where we capture our data on Earth. I mean, it could also be a spaceborne telescope that we use as a ground station, which is compared to Alpha Centauri ground. Then.
But we are spoiling someone else.
Yeah, but I mean, like it will be a great loss, and the optical wave can place a lot. Back to the Earth. So why don't you just use like a relay satellite or something before reaching the Earth directly? So
that might be useful. Yeah.
It's one of the options, actually.
Was one of the options.
Anybody else? I've got a question. In your report, you had a nice cat drawing.
Yeah,
of
sorry,
your
we couldn't
spacecraft.
put it here.
We missed it here.
Because you have a slide with it.
Yeah,
I saw a slide.
no, there's nothing. I mean, yeah.
Yeah,
Oh,
yeah,
yeah. Oh, okay. Sorry.
I
Yeah,
mean,
talks about
that's the
little
thing
bit
people
variation.
always want to see.
Yeah, so that's our spacecraft.
Can you explain it, maybe?
Okay, so all the instruments are, you can see that it's on these cylindrical hexagon. Hiya then. Or, well, here. Okay, so here the instrument will be based here. The idea is the RTG3, we require 3 RTG due to our power requirement. And so it's been placed away from the instrument, tried to. And because this would be the shield that would, protect from the high speed, from the dust and everything. And this is the maxilla, and the, so this is like stoved maxilla, and the laser sail is not in view. Yeah. So
I was just wondering from a thermal engineering perspective that usually you place the RTGs in a way that they are looking into free space because otherwise you cannot reject your thermal radiation. And in that case, I can understand the heat shield will probably be like jettisoned at a certain point, so this is probably not an issue. But want to place the RTGs maybe, I don't know, far away with a
well, we can do that. I mean, you can put
one of the main problems, I think, was also the possibility that the payload will freeze during the cruise. So maybe the heat that the RTGs is quite a lot. They're just heating, warming up maybe a bit the space. So it has to be done more work about the disposition of this. Because one of the idea was also that since the RTGs decay quite quickly considering the time of the mission, we wanted to put them also in a place where we can eject them in the case one decays faster, and to not carry with us dead weight. We wanted to eject it, but the main position has to be really decided right now.
I mean, I think ejecting the RTGs doesn't make a lot of sense because the decay is similar for all 3 of them. So if you eject them, then there's no stage.
It's only a precaution in the case something goes wrong. For example, if one of them starts to give massive problems to the entire spacecraft. In the emergency system related to the power system, there is also the possibility of checking all the circuit. When you start to have problem with the power source, you can eject instead of compromising all the mission.
Okay.
If you just in the report there is all the subsystem on the software.
And just a very quick comment about the RTGs. I mean, the thermal power which is generated by the RTGs and which is not converted into electricity, it's really significant. And this is like, I don't know, kilowatts sometimes.
Yeah,
range of kilowatts. And if you don't face free space, you will heat up your structure in some way, and then at a certain point it will simply melt. So I think the problem is not that the spacecraft gets too cold, it's rather making
the other one,
So this structure on the back, this is your cell/mag-cell configurations at the yellow bit at the back.
Yeah.
That's just a schematic to represent where the cell,
where it would
and
be
the thickness is exaggerated, is it? In the drawings?
Well, it's just, I mean, that's the stoved one. It's not deployed.
Okay, so that's the whole right. So what's going on? It looks like you've got some sort of actual orientation thing.
The joint.
So that's for winching and things.
Yeah.
So is that going to cause structural torques doing it from the centre like that?
Interesting.
The problem extensive analysis.
Extensive analysis instructors were quite
really presented here. It is just in our report an idea how we will move a bit if we need to.
We hope not to.
Any more questions?
No,
okay.
Thank you.
Okay, break time. welcome folks. In a short while the final review panel will be disappearing to make the final decision. I think they have a tough job. And I will ask the students to fill out a survey form for us to get some feedback on
Just a few words about the evaluation process, because I haven't talked about that before. So the evaluation process consists of two parts. So one part, the first part is based on the reports. So you have sent in your reports, and these reports were reviewed by international experts. So I think there were like 6 or 7 of them, and they graded your reports based on the criteria which were in your requirements documents. So the first criteria was feasibility with respect to the requirements. Second one was analysis of key feasibility areas. So have you actually assessed the key feasibility areas of the mission? And the third was the correctness of this feasibility analysis. And the fourth point was the depth of detail of your analysis. And fifth point was innovation potential. So are there any ideas that are promising and make an interstellar mission like that feasible in the future? So these were the 5 criteria with respect to the report. So now our review panel will look into or will evaluate your presentations and how you handled the Q&A session. And these are 2 additional criteria which will assess afterwards. And then we will count all the points from all these criteria and then decide upon who will be the winner or the winners of this competition. Okay?
Okay, so I will kick the review panel out in sort of 15 minutes or so and ask them to retire. Unfortunately, I'm going to ask the teams to stay in this room because they're going to have to retire out to the lobby there. The room we're going to use is not usable at the moment. So take a break, continue your conversations, and see you all soon.